Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Amirul Ridwan bin Rahim, and this is my member group Muhammad Harid Imran bin Hamdan and Shahmikli Deni Hanini bin Syari Adnan. So today we will present about experiment heat pump. So main objective for this experiment is to demonstrate the principle of heat transfer in exchanges, to the principle of a refrigeration cycle, to demonstrate the principle of a heat pump cycle, and to use the refrigerant diet sheet and pH chart. For the experiment, we will use apparatus like water heat pump unit, stopwatch, and measuring cylinder. For this experiment, we have two parts, part A and part B. For part A, firstly, we turn on the main water supply and by a process of trial and error, set the evaporator and condenser water flow rates. The coil in both brackets A and B had to be fully immersed under water at all times. The condenser flow rate was kept as low as possible. Care was taken not to overflow the buckets. Second, place all the thermometer in the proper point as shown in the schematic diagram in figure 1. Third, measure the condenser and evaporator inlet temperature Tc in and Te in. Use the measuring cylinder and stopwatch to measure the condenser and evaporator water mass flow rate (mc) and me for 1 minute. Measure the condenser and evaporator outlet temperature (Tc and Te out) and the initial reading of all the other thermometer and pressure gauge, and record all the readings in the table 1. And lastly, switch on the compressor and repeat step 4 every 5 minutes until pressure was about 10 bar gauge, and record all the data in table 1. For part B, when the pressure was about 10 bar gauge, increase the condenser and evaporator water flow rate in and modify the water outlet in both condenser and evaporator with to maintain a steady flow rate. Second, repeat the measurement as in step 3 in part A for 60 seconds of water collection and step 4 every 5 minutes. Third, repeat step 1 once or twice or until the condenser water flow rate was too high about the overflow. And lastly, took snapshot, observe and recorded the observation of the refrigerant inside the viewing glass A and B.
So for the data, here we have part A, in which we constant the MC 0.17 kilogram per second, for ME 0.26 kilogram per second, T condensed in plus minus 25 degrees Celsius, and T evaporation out at plus minus 27 degrees Celsius. Below is the data we collected throughout the experiment. Here is the part B data, in which we vary the MC and ME to get the T evaporation and T condense for each data we have. So we need to do this like 5 times along with part A. We need to do 5 times, but the difference is part B we start with the timestamp at 5 minutes instead of 0. So here is the images that we managed to capture during the experiment, which is viewing glass A and viewing glass B. It is worth noting that in viewing glass B, the air bubbles are actually more visible than in the viewing glass A. So here is our verified data from our lecture. So everything has been explained from the previous slides. So for data analysis, we can actually calculate Q evaporation and Q condensation from the time and the TC and TE we gained from part A. So after we got all the Q evaporation and Q condensation, we can now calculate the average Q evaporation and average Q condensation for each of the data. So after we got the average Q evaporation, which I already calculated, we get 2.90 kilowatt, and average Q condensation is 3.52 kilowatt. With these average numbers, we can now calculate the average coefficient of performance, COP, by using the Q condensation divided by Q condensation minus Q evaporation, which will get 5.68. For part B, we need to find the same thing, which is Q evaporation and Q condensation from all the data we have and the equations given in the experiment. So we will get the average Q evaporation for part B to be 4.49 kilowatt, and average Q condensation for this part B is 10.14 kilowatt. With the same formula, we can calculate average coefficient of performance 10.14, which is average Q condensation divided by Q condensation minus with Q evaporation, which is 10.14 minus 4.49. We will get the average coefficient of performance, COP, at 2.07. So here is the graph at t equals to 5 minutes. Next, we have the graph at t equals to 10 minutes. Next, we also have the same graph, but with t equals to 15 minutes. This is the graph in which t is equals to 20 minutes. And lastly, the same graph, but with t equals to 25 minutes.
In this experiment, we conduct two parts of heat pump cycle, which is evaporation and condensation, observing various parameters including flow rates, temperatures, and pressure. The core objective was to understand how heat is transferred through the refrigerant and the principle governing the refrigeration cycle. Part A of the experiment focused on the setting correct for water flow rates in the evaporator and condenser to ensure effective heat exchange. The data showed a noticeable decrease in temperature evaporation as the process continued. In Part B, the system was further adjusted to achieve steady flow rates. The modification ensured that the water flows was controlled and the flow rates were optimized for efficient operation of the heat pump. The data analysis revealed that the average coefficient of performance COP for the system in Part A was 5.68, while in Part B the COP was 2.07. This disparity can be attributed to change in system condition, such as flow rate adjustment and the temperature variation. In Part A, the heat pump performed better, likely due to more stable condition. In contrast, Part B showed a slightly less efficient performance due to higher flow rates and more complex operational condition. For the conclusion, the experiment successfully demonstrate the principle of heat transfer, refrigeration, and heat pump cycle. The result reflect typical behavior of a heat pump with different COP values indicating the efficiency change based on operational condition. Further improvement in system control, particularly in maintaining optimal flow rates, could enhance performance. The analysis of the COP in both parts highlight the importance of the understanding operational adjustment and their impact on the energy efficiency in heat pump system.